Good morning, students. Today we'll start the topic orthogonal complements and direct sums. So first of all, we discuss some basic definitions related to the topic. So the first definition is the distance of an element from a non-empty subset in an inner product space. So let us consider X D be a metric space and X is an element of this metric space X. Let us take M is non-empty subset of X. Then we define the distance of this element X from the set M. This is denoted by D, distance between X and M, and this is defined as the infimum of the distances of all the elements of the set M from this element X. Means we can say infimum of distances of X from M, where this M belongs to M. So we find out the distance of all the elements of M from this X and take their infimum. This we have denoted by delta here. Now we know that in an inner product space we can define norm by the formula distance between X and M is equal to X minus M norm. So in case of norm spaces, this distance can be defined as delta is equal to the infimum of the norm of the difference of X and M. So in this way we can define the distance of an element from a non-empty subset in a norm space. Now next definition is what is segment. If we take a vector space X and we take two elements X and Y belonging to this vector space, then the segment joining the two elements X and Y is the set of all those elements belonging to X which are of this form: alpha X plus 1 minus alpha into Y, where alpha is a real number and alpha belongs to the closed interval 0 to 1. So this kind of elements, they form a segment. Next is the definition. What is convex subset? Let us take X be a vector space, M is a subset of X. Then we say that M is convex if we take two elements from the set M, then the segment joining these two elements that is contained in M. Then we say that the set is convex. For example, if we take a vector space X and we take its subspace, then we, by definition of subspace, if we take X and Y belonging to subspace, then alpha X plus 1 minus alpha into Y, that will belong to the subspace. So we can say that the subspace in a vector space, that is a convex set. Next is a theorem. The theorem is minimizing vector theorem. The minimizing vector theorem. Let us take X is an inner product space and M is non-empty convex subset of X. We are given that this is a complete subset in X. This is complete in the metric which is induced by the inner product. Then we are to prove that for every X belonging to X, there exists a unique Y belonging to M such that delta, which we defined already, delta is the infimum of the norms of the difference of X from all the elements of M. We can say that delta is the infimum of the distances of all the elements of M from X, which we have defined already. We are to prove that there exists unique Y for which Y is the infimum of X minus Y bar, where Y bar belongs to M. This is further is equal to X minus Y norm. So we are to prove the uniqueness of Y. Firstly we will prove the existence of Y, then we prove the uniqueness of Y such that delta is equal to X minus Y norm. So we have to prove this condition. This theorem is called minimizing vector. Now let us first of all prove the existence of element y which belongs to M. So in order to prove the existence, let us start from the definition of delta. Now what is delta? Delta is the infimum of the distance of x from all the elements of the set M. So by definition of infimum, there will exist a sequence which we have taken yn, this sequence in M, such that this sequence converges to delta. So we have taken delta n converges to delta as n approaches to infinity, where delta n we have taken the norm of x minus yn. Now let us take Vn is equal to yn minus x for every n. Let us find the norm of Vn. Now norm of Vn means norm of yn minus x. Now norm of yn minus x we have denoted by delta n. So this is delta n. Now let us consider the norm of Vn plus Vm. Now Vn is this term. So Vn plus Vm means Vn is yn minus x, Vm is yn minus x. Substituting the values, this will become norm of yn plus ym minus 2x. Now we can take 2 common from this norm. Taking 2 common, inside we are left with 1 by 2 times yn plus ym minus x. Now because yn and ym they belongs to the set M and M is convex, therefore the line segment joining yn and ym that also lies in M, and we know that the distance of all the elements of y from the distance of all the elements of M from x, that is having the infimum value as delta. Because delta is the infimum of all such distances, therefore this will be greater than or equal to delta. So therefore this quantity is greater than or equal to 2 delta. Now let us consider yn minus ym norm square. Now adding and subtracting x here, this can be written in this form. Now yn minus x, that is Vn, ym minus x, that is Vm. So this quantity will become Vn minus Vm norm square. Now Vn and Vm, these are the elements of the inner product space X, and X is inner product space, and in this space we can use parallelogram inequality. So by using the parallelogram inequality, we have parallelogram inequality x plus y norm square plus x minus y norm square is equal to 2 times x norm square plus y norm square. Here x and y are replaced with the elements Vn plus Vm, Vn and Vm. So by using Vn and Vm in place of x and y in parallelogram equality, we get Vn plus Vm norm square plus Vn minus Vm norm square is equal to 2 times Vn norm square plus Vm norm square. Now Yn minus Ym norm square, here we can put the value of this expression here. Putting the value Yn minus Ym norm square is equal to 2 times Vm norm square plus Vn norm square minus Vn plus Vm norm square. Now substituting the value of Vn plus Vm norm which we have already obtained, Vn plus Vm norm is greater than or equal to 2 delta. So if you multiply with minus sign, that will become less than or equal to minus 2 delta. So putting here the value, and Vn norm, that is delta M, and this is delta n. So substituting the values here, these are as n approaches to infinity, delta n approaches to delta. As m approaches to infinity, delta m is approaching to delta. So this will become delta square plus delta square, 2 times delta square plus delta square minus 4 delta square. So this will approach to 0 as n and m approaches to infinity. Now because the sequence yn is a Cauchy sequence, from here we have obtained, and because the sequence is in M and M is complete, it is given to us, and if a space is complete, every Cauchy sequence in that space converges. So every Cauchy sequence in M will converge